So we have some interesting agenda today. Device current equation for NMOS. Then power dissipation in CMOS logic. We have been repeatedly talking about this thing in our part B practicals. P equal to so many microwatts. And third is design layout rules. So design layout rules is as such not a part of syllabus, but then we are already using it, so we need to know about it. So you have already done this thing in second year when you studied about MOSFETs. And I'm quite sure that university must have put the derivation of the expression for device current IDS. So still to recall, we are going to just put down the equation and denote the important terms. So when we say device current in a MOSFET, we actually mean a drain current or the drain to source current. So device current is denoted as IDS for NMOS. And we will discuss about what will be the expression for IDS if we consider a PMOS device. So the general equation for the drain to source current in NMOS device denoted as IDS is given by IDS is equal to mu n, so epsilon ox upon T ox into W by L into VGS minus VT into VDS squared by 2. Okay. So sometimes it is also written like this. Equal to so this is the parent equation, and we can define the terms now. Mu n is the electron mobility expressed in centimeter square per volt second. W L and TOX represent the geometry of MOSFET. Specifically width, length, oxide thickness, epsilon ox is the permittivity of SiO2 layer, which is equal to epsilon 0 into epsilon r, which is equal to 3.9 times epsilon 0, since epsilon r is relative permittivity of SiO2 is 3.9. VGS, VDS are the gate to source and drain to source potential differences. VT threshold voltage of MOSFET, and when we discuss about body effect, we have actually written the equation for VT. So I think so, if you remember, it was equal to VT0, this parameter, and last but not the least, this factor VGS minus VT is also called as gate overdrive voltage, or VOD. So basically we know that for complete inversion under gate terminal, that is formation of channel, the necessity is VGS should be greater than VT. So this difference VGS minus VT, it tells us how much is VGS in excess of VT. Okay, so that is what is called as gate overdrive voltage. Why? Because it indicates VGS in excess of threshold voltage. So gate overdrive voltage. Now we again come back to equation number 1 and we have to combine some terms now. Okay. considering equation number 1 again, we have IDS, electron mobility, into epsilon ox upon T ox, W by L, VGS minus VT into VDS minus VDS square by 2. So, which is equal to mu n into C ox into W by L into VGS minus VT to VDS by 2, where C ox is epsilon ox upon T ox. Okay. So this is called as gate capacitance per unit area. Why COX is called as gate capacitance per unit area? The answer lies here. We know that capacitance C is equal to epsilon A upon D. Okay, and applying equation number 2 to the 3D planar structure of MOSFET, we can say gate capacitance Cg is equal to epsilon ox into W into L upon T ox. So we know these things now from 3D planar structure of MOSFET. The gate capacitance is equal to the permittivity of SiO2 layer into area of MOSFET, that is W into L, upon the distance of separation is T ox. Now we also know that since W into L is area of MOSFET, we can say that Cg is equal to epsilon ox into area upon T ox. If the area is 1 unit square, then Cg will become equal to epsilon ox upon T ox. Okay, so thus C ox is equal to Cg for area equal to 1 equal to epsilon ox upon T ox. Now you got it? Why this term epsilon ox upon T ox is called as gate capacitance per unit area? Because the gate capacitance is equal to the permittivity of silicon oxide SiO2 into the area of MOSFET W into L upon T ox. So since W into L is area, for area equal to 1 unit square, my expression for gate capacitance boils down to epsilon ox upon T ox. That is why we have replaced this with C ox. Okay. So now we have to name this equation as something different. So we say this is equation number 2 equation 3, equation 4, equation 5. Okay, so returning to equation number 2. VGS minus VT into VDS minus VDS square by 2 is equal to K dash into W by L into VGS minus VT into VDS minus VDS square by 2. This will be equation number 6. Where K dash is equal to mu n into Cox. Again, we have IDS is equal to beta into VGS minus VT into VDS minus VDS square upon 2, equation number 7. Here this is asked in Viva. Beta is called as gain factor, not the gain factor of MOSFET. Okay, so we will do the highlightings afterwards. Okay, so from equation number 1 to 7. Okay, fine. So it is very, very important for you to memorize this equation for IDS. We can have a last note on this. Equation one assumes different forms depending upon the relative values of VDS and VOD, that is overdrive voltage. Okay, equation number 1 assumes different forms depending upon the relative values of VDS and VOD, which determines the operating region of MOSFET. Okay, now we come to the second topic, power dissipation in CMOS logic. Okay. There are some important observations which you must have done, because already you have studied, different circuits and different systems right from second year of engineering. So some observations which all of us have done while we have graduated from second year to final year is that any digital system can be subjected to at least two different kinds of operations. The first is called as static, and second is called as dynamic. So while static and dynamic can be defined in different ways, one way of defining static and dynamic is that if the inputs change randomly, so in static systems, the inputs to the system change randomly or at a slow non-periodic rate, or else they remain constant for a fairly good amount of time. Okay, so when inputs change randomly or in a slow non-periodic rate, or they remain constant after a change for a good amount of time. For example, you take example of an AND gate. So a 2-input AND gate can have any input combination from 0 0 to 1 1. So for example, at some instant of time, AND gate has inputs equal to 0 and 1. So now for 0 and 1 inputs, AND gate's output is 0. So now the first input changes from 0 to 1. So the output changes from 0 to 1. So you see the inputs are changing randomly, and once they change, they do not change for a good amount of time. That is called as static operation. On the other hand, if inputs change periodically and at a high frequency rate, it is called as dynamic system. Okay. So in dynamic systems, inputs change periodically and at a high rate. Okay. For example, if you apply two different frequency clocks to an AND gate, it becomes example of a dynamic system. Okay, going ahead. Now, if we see the history of IC design or processes right from 1971, we already told before that speed, area, and power, these are called as VLSI design metrics. That is, if we design any VLSI system, we always ask a question: what is the speed of operation, how much area it is occupying on the wafer, and how much is the power consumption and power dissipation. And if we see that before a few decades, the focus of any IC which was launched in the market was only speed and area, and nobody really spoke about power. Why? Because power dissipation was less. So the aim before some years was to increase the speed as much as possible and reduce the area as much as possible, and nobody really spoke about power. But what has happened is, over the years, the number of transistors fabricated on chip have increased, and also the operating frequencies have increased. So we can say, due to increase in transistor count and operating frequencies, the power dissipation has not increased. We can say it has skyrocketed. This is the right word. It has increased like anything. That is why we see that even Intel and AMD, when they started competing before few years, that is after 2005, their focus was never the operating frequency in gigahertz or the area, but all of them started working on power optimization. That is why I always mentioned before that all Intel's architectures after Haswell, Haswell and the lake architectures like Rocket Lake, Ice Lake, Tiger Lake, Coffee Lake, all these are actually aimed at, they're all aimed at reducing the dynamic power dissipation of chip. Okay, the point. So it's very important for us to understand, right? So now the aim of this discussion is to actually come to a mathematical model which can help us decide that what does the power dissipation in any CMOS system actually depend upon. So we want to derive a mathematical model. Okay, so let us define some basic terms. So let us assume this system so this is a CMOS system. It can have any functionality, right from as simple as inverter to as complex as a microcontroller. This CMOS system will accept set of inputs. It will generate a set of outputs. Naturally, it will be driven by a bias voltage VDD and there will be ground. This is an example of a CMOS system. Okay, so we can also say that the current drawn by the system as a function of time is IDD of T. Because there is switching involved, combination systems form only 10% of the microprocessor's logic and remaining 90% is all sequential. That is why when we say sequential, it means clocked. When we say clock, there is frequency. When we say frequency, it means there is switching. That means what? The current drawn from the supply is never constant. It varies as per the switchings involved inside the CMOS system. That is why we define VDD as a supply voltage in volts and IDD of T is a function of supply current drawn from VDD as a function of time. So now the first term which we would define is the instantaneous power. P of T. So instantaneous power P of T is equal to the supply voltage VDD into the supply current as a function of time. Let this be equation number 1. Second important term is energy consumed from supply over an observation interval T1. So T1 is the observation interval for the power dissipation in a system. Energy consumed from power from supply over an observation interval T1 is given as E of T is integration 0 to T1 VDD into IDD of T dt. Let this be equation number 2. And last is the average power consumed from the supply. Okay, so we can say average power over interval T1 is PAVG is 1 over T1 integration 0 to T1 VDD into IDD of T dt. Okay, so we have instantaneous power PT, energy consumed E of T, P of T, and we have average power P average. These are basic terms which will be used for mathematical analysis soon. Okay. Now, the next part is, what are the different components of power dissipation? This is again a very favorite Viva question. So we can say components of power dissipation. Power dissipation basically has two components. One is static and one is dynamic. And there are many contributing factors to static power dissipation. The first is sub-threshold current through off transistors. Okay. Second is tunneling current through SiO2 layer. We already mentioned Fowler-Nordim tunneling, that is when TOX becomes less than equal to 2 nanometer. At that time, tunneling current, actually the gate current should be 0, but it starts becoming non-zero. The third factor to static power dissipation is leakage through reverse bias diodes, and fourth is contention current in ratioed circuits. Okay. And as far as the contributors to dynamic power dissipation are concerned, the first major factor is charging and discharging of load capacitance CL, and second is short circuit current. We can say short circuit current because of not T on, we can say turn on and turn off times are not equal to 0. You also know this as cross conduction or shoot through fault. We have seen this cross conduction current in CMOS inverter when we saw the voltage versus current waveforms in microwind tool. So we had spikes, current spikes were shown, which indicated current flowing between VDD and ground every time that PMOS and NMOS were switching states between each other. So because of static, what we get is static power dissipation, and because of these two factors we get dynamic power dissipation. So static power dissipation. So for explaining both static and dynamic power dissipation, we are going to consider a CMOS inverter circuit. Consider CMOS inverter circuit. PMOS is P, NMOS is N, and we know that input can be 0 or 1. Okay, so for Vin equal to 0, P equal to on, and N equal to off. So this circuit will simply look like PMOS is on, NMOS is off, and here we have 0, okay, at the gate. Okay, so this is my P, this is my N, and my output is equal to strong 1. We see here in this case IDD is equal to 0 amperes. And similarly, when Vin equal to 1, PMOS is off, NMOS is on. Circuit now looks like this. And the output is equal to 0. So again we see here that IDD equal to 0 amperes. So in both the cases we see that the power consumed from the supply is 0. So we can say P equal to 0 watt, and here also P equal to 0 watt. Why? Because there is no current flowing between VDD and VSS terminals. Okay, so here okay, so we can say ideally P static equal to 0 watts. So ideally P static is 0 watts. Okay, but here we are not considering these 4 factors which we just mentioned. Okay, that is why we can say that ideally P static is 0 watts, provided the 4 contributing factors are absent. So static power dissipation is 0 provided the 4 contributing factors, that is subthreshold current through off transistors is 0. There is no tunneling current through the gate oxide layer. There is no leakage through reverse bias diodes, and there is no contention current in ratioed circuits. So if we consider that the current through these 4 factors is not 0, then it is called as I leakage. Okay, so understand one thing, that these 4 factors contribute to what is called as I leakage. Okay, so we say that practically I leakage is not equal to 0. Therefore, the static power dissipation is equal to 0 watt, or it is equal to VDD into I leakage. So we say this is ideal, and here we say it is practical. Okay, so we say that CMOS logic family is a zero power family. Okay, but this statement is both true and false. So in Viva, always ask a question to the students that, okay, do you agree with this statement that CMOS logic family, do you agree with the statement that CMOS logic family is a zero power family? The answer is true and false, because if we consider static power dissipation, then under ideal conditions with no leakage current, yes, the static power dissipation is 0. So in from that perspective, CMOS logic family is a zero power family. But if we consider dynamic power dissipation, then it is a non-zero power family, because in dynamic power dissipation, the dynamic power dissipation is proportional to the operating frequency, and in the world of VLSI, you will never have operating frequency as 0. Always there are switchings. So CMOS logic family is a zero power family if we consider ideal static power dissipation. It is a non-zero power family if we consider practical static power dissipation. It is definitely not a zero power family if we consider dynamic power dissipation. Got the point? So considering ideal conditions, we say that CMOS logic family is a zero power family. If we consider ideal static power dissipation. Okay, if we consider ideal static power dissipation. Okay, understand the leakage current is very less. Okay, so we can put a comment here that leakage current is few nanoamperes, hence P static is almost equal to 0 watts. Okay, why? Because if we consider 90 nanometer technology, then VDD is 1.2 volts, and if the leakage current is say 10 nanoamperes, then naturally the static power dissipation even in practical conditions will be only 12 nanowatts. It's almost zero. Okay, so even if practically the static power dissipation is non-zero, still it is almost zero because the leakage current is only few nanoamperes. So we can very confidently say that for all ideal and practical conditions, yes, CMOS logic family gives zero power dissipation. It gives zero power dissipation. Okay, so we can say considering very low values of bias voltage and high leakage, P static can be approximated to 0 watts. Okay, so we do not have time for dynamic participation. We will take it in the next lecture. Okay. Okay, fine. We have 5 minutes. I thought it's over. No issues. We'll continue. So dynamic participation. As we told that dynamic operation means the inputs are actually changing dynamically, that is periodically and at a high frequency. So again what we do is consider a CMOS inverter driven by a clock having frequency FCLK. Okay, FCLK, and driving a capacitive load CL. Okay, so here we have we can also call this ground. Here we have V in and it is a clock. The frequency is FCLK. Okay. So here we can say that when V in equal to 0, Cl charges from ground to VDD, and when V in equal to 1, Cl discharges from VDD to ground. This is because P equal to on, N equal to off, and here P equal to off, N equal to on. Okay. Okay. We'll continue the remaining derivations in the next lecture.